So first of all, of course, it's a great honor to be here. Thanks a lot for the invitation. Thanks, Martin, for all the inspiration, all the work, all these years. And of course, thanks for the opportunity to give a talk next to all these great speakers that have spoken before me, and Patrick that will speak after me. So what I want to do, I just want to briefly talk about the times that we have ahead of us, which I think are very interesting. And I think one of the best way to do this is to do it in the context of what Martin has been for databases, right? And he's definitely a renaissance man. So he has pioneered and continues to come up with great ideas, very creative, has been mentioned by everybody who has spoken so far. So I'm not going to repeat it, although it will be really well deserved to repeat it over and over again, right? Now, to me, what is even more interesting is that he did this at a time where you don't need to have been around for too long to realize that not very long ago, the database landscape, both in academia and industry, was really dominated by the big engines, right? And it was very difficult to actually come up with a new engine, come up with a new ideas, because they will tell you, well, DB2, Oracle, SQL Server, Teradata, they already do this, they all work. So no point in trying to come up with anything crazy. So I see the people who were working at those times and still were able to come up with valuable ideas, and not only valuable ideas, but ideas that actually came across and became established, right, as especially courageous. What we are now today is a very different time where in database research, almost nothing is cast in stone. People are completely redesigning engines. People are completely rethinking database data processing, both in the cloud, new hardware, and so forth. We have already heard some of those ideas, applying many database ideas in other areas. And this is an era where we really need the creativity that Martin has had until now, and I hope that he will continue contributing to the database community, right? Many of these ideas, because we are at a phase where we really need to come up with new inspiration in order to go in different directions. So the reason why I'm saying this, and this is a theme that has been, in my mind for already a few years, is that specialization is on the rise. So general purpose is history. Again, you don't need to be too old to realize that until a few years, most of the computer systems and most of the software used to be general purpose, operating systems, databases, a lot of infrastructure used to be general purpose. This is no longer the case. Today, specialization is the name of the game. And there are many reasons for this, and we could spend a whole day talking about it. But I think the biggest game changer these days is cloud computing. So cloud computing is not just a platform, it's not just about the hyperscalers. It is actually a change in business model, very fundamental change in business model. It's turning IT into a service industry instead of being a manufacturing industry. It is dominated by a few hyperscalers. Very few companies really dominate the market. The economies of scale are something that we have not seen before in terms of the size of the cloud infrastructure and so forth, right? So this actually is leading to the specialization, because in this context, you can actually go and build what is best for the job, right? And conventional computers are not really what is best for the job, to a very first approximation for actually many jobs. So this is actually something that is actually making a big impact and making a big differentiation in how things are evolving. So there are many examples. I don't want to spend too much time on it, because people have discussed this many times. There is the Google Tensor Processing Unit. There is Microsoft Catapult that actually uses an FPGA and it puts it on the network path. And Amazon just announced what you see on the right side of the slides, just announced this Amazon Aqua, which I find it a very interesting design, which in essence what it uses is an FPGA attached to or next to a network interface card, where you can actually go and deploy part of your queries and filtering and all those sort of things, right? So that you can actually optimize the flow of data from Amazon S3, where you actually have your storage engine, so to speak, to the compute nodes, right? And they already use in Redshift. So this is already an application, unlike the Google's TPU, which is mostly for machine learning, or Microsoft Catapult, that until now is mostly for infrastructure. Amazon CWI is actually an application that actually is very, very close to databases, right? You can actually claim that ideas like this have been around for a while, but you actually see these things, this specialization coming up, right? I mean, in very clear ways, and this will continue. I mean, this is not going to stop here, it will continue. And this is not just the big companies. So what is happening is that, of course, now all the cloud companies are putting all this fancy hardware and making it available, like Amazon has done with FPGAs and so forth. So you see actually many companies trying to use this, right? In our case, because we have been working with FPGAs for a while, we are privileged to have the opportunity to work with quite a few companies that are interested in trying to explore this type of architectures, right? So for instance, with Amadeus, we have been using the Amazon F1 infrastructure to actually speed up their search engine in a variety of ways. And we have been reasonably successful with it to the point that Amadeus is now turning this into a product. So you see that this tendency towards a specialization, right, going away from having something specialized, but if you have a workload that is big enough and that is important enough, specializing all the way down to using something like as specialized as an FPGA is now becoming the norm rather than the exception. So what I want to do is I just want to spend a few minutes thinking about what will be, or what is the implication of this for databases and what will be in the future. And I, like many in the audience, I'm a professor at university, so I actually teach database architecture and database systems and so forth, right? If you look around, what most of the things that we teach have not changed much over the last decades, I would say. In reality, a lot of these things that we're teaching I don't believe that they're going to be in place 5 or even 10 years from now, just because of the different architectures, right? So what I have on the slide is just a picture that is actually showing what you will have typically on the cloud, augmented with a few things that are starting to appear, but maybe they are not as common or people are not that much aware of it. So what you have is a separation between compute nodes and storage nodes. Instead of having a normal network, what I have added is a smart NIC, so a NIC where you can actually process data, both on the compute nodes, but also on the storage nodes. And in between, I have a smart switch, an application-specific network. Eventually, this is going to be a programmable switch where you can actually put application logic and so forth, right? And then the compute nodes are going to be a mixture of CPUs, GPUs, tensor processing units, FPGAs, and so forth, plus a weird combination that I think nobody really understands today between normal memory, DDR, DRAM, non-volatile memory, SSDs, potentially hard disks, and so forth. Okay. So if you look at something like this and you think about what a database does, you can start thinking about doing a lot of things. You can, for instance, imagine moving anything that has to do with filtering, compression, encryption, schema mappings, extract, transform, load, formatting, search, even maintenance of views and things like this. You can actually push them down all the way to the storage node. So the compute nodes will not do anything like this. Imagine something like providing views directly on the storage as opposed to actually having to materialize a view at the level of the compute node. If you look at the network, you can start doing content-based routing. So instead of actually having to take data and then having to do something fancy to partition the data across nodes, you could actually do this potentially on the switch. You can do hashing, partitioning, compute data statistics as the data flows by. You could actually even check consistency by keeping track of where data is and then validating caches and so forth. And this could actually be done in a much more efficient way than we're actually doing, because you will be pushing down this on the infrastructure as opposed to having to do it everything at the level of the database engine. And then, of course, in the compute nodes, we are going to have a very sophisticated architecture where you can actually use a lot of this fancy hardware to do things like memory routing, view materialization, synchronization, consistency, more filtering if you want to, right, and so forth. So if you look at this picture, which is just an approximation, right, and I don't want to spend too much time on it right now, because I mean you could really spend here taking a conventional database engine, taking it apart, and then try to map it to this architecture. You see that you will start seeing a lot of the features that typically we imagine a database engine providing are now going to be spread all over the cloud in this particular case, all the different parts of the cloud and so forth. So in our case, and just to sort of give you an idea that I think in a very modest way is at the same level of craziness as sort of Martin's ideas over the years, because we were very interested in these notions that I have just explained about acceleration and so forth. We decided, well, it is very unlikely that we are going to have access to Microsoft's cloud or to Amazon infrastructure. We know that all these people are building hardware like crazy. Why don't we go and build our own computer with the goal, among other things, not only databases or data processing, but also with the goal of actually giving ourselves a platform where we have much more flexibility to explore what the hardware can do. And this is Ancient. This is joint work with my colleague here at ATH in Timothy Roscoe. Some of you have seen already this announced because we have been working on this already for quite some time. Ancient, for those of you who have never seen this, is a platform where we combine multi-core processor, in this case, an ARM processor with 48 cores. We have an FPGA on it. A very important thing on this FPGA is that we have half a terabyte of memory associated with the FPGA, which is enough to actually do very serious data processing. Now you don't have to actually put the data on the memory of the host, but you can actually have the data directly on the FPGA. Many databases will actually fit inside the FPGA. And then we have a number of interesting peripherals, like we have 4 times 100G network, so you can actually have a lot of connectivity to this, plus and a bunch of other additional interfaces like PCI, non-volatile memory, and all those sort of things. And this is actually, I'm happy to announce, and this is the announcement that I'm making here, because I assume many of you do not actually follow this, is that now this is actually real. We do have the board. The boards are already into their chassis and about to be mounted on a rack. So this is actually now something that is real. These are machines that are running, and we hopefully soon to have a cluster of these things fully deployable, not only in terms of the hardware, but also with the proper software to actually do work on top of them. Now, again, I don't want to spend too much time discussing many possibilities because I have done this in other occasions, and maybe we can actually spend some time discussing these possibilities, which is probably more interesting. Let me just give you one example of what you can do with this that is actually borrowed from an idea from Oracle. Oracle has this M7 processor, one of these Spark processors, where what they did is they took a multi-core processor. This is what you see here. The multi-core processor has the standard many cores in different sockets, then it has memory, and then between the memory and the sockets, there is accelerator, right? There is an accelerator, near memory accelerator that you see in there, this MCU. And then what this actually does is, well, it does a bunch of things, right? For instance, with security, it also does some things for checking memory accesses and controlling that you're not going to parts of memory that you're not supposed to go. But one of the things that it does, which of course for the database audience will be very interesting, it actually moves part of query processing to the path between memory and the CPU. And of course, this is very interesting because even the most basic database operation, like running a selection operation, is extremely inefficient from the point of view of hardware. You're grabbing a table with maybe 1 million tuples, and you're taking all those million tuples, you're bringing them to the CPU just to select one of them if you don't have an index, right? And that's a huge amount of data movement. What this architecture allows you to do is actually put the predicate here on this accelerator and then catch the data as it moves from the memory to the CPU. And you are not polluting the caches. You're actually doing this closer to memory, so it has significantly performance advantages. So in Ancient, we can do something like this. As I said, we do have half a terabyte of memory on the FPGA. So one idea, one possible design that we're already exploring is actually putting the database in the memory of the FPGA and use the FPGA as a data mapper, something that actually provides these transformations as you actually want to process the data from the CPU, okay? Now, an aspect that I have not mentioned, just in the interest of time, that it makes Ancient interesting is that the connection between the CPU and the FPGA, has always been done through PCI, and this is typically true in many systems. In our case, it's actually not through PCI. It's a cache coherency interface that has 30 gigabytes per second bandwidth, so it's significantly faster than PCI. In the future, of course, hardware is evolving very quickly. There are, Intel is coming up with new ideas, Gen Z is coming up, right? So we'll have more bandwidth in there. So this notion of actually having the memory of the FPGA as the place where you have the data, and with the FPGA acting as a near memory processor can actually be very interesting. Okay, so just to sort of wrap up and finish here so that there is time for some questions, let me also try to sort of throw a couple of other ideas so that you see the potential. And this is something that we're thinking about doing, but for lack of enough people and time, we have not yet started doing. But I want to sort of use this as an example of what hardware does, right? That a lot of people in the database community have not necessarily realized yet. So this is actually work that we just published in the last BLDB, where we actually took the Gray and Reuter Black Book of transaction processing. We implemented the log manager, essentially the transaction manager that you have described in there, which is a relatively classic one with a hash table for logs and things like this, right? We partitioned this. And the only thing that we did that it was a little bit fancy is that we actually ran this using RDMA, and then we deployed this on a supercomputer. We went all the way down to all the way up to like 2048 nodes. And this is what you get for different forms of locking mechanisms, timestamp ordering, two-phase locking in different versions, and so forth, right? So what is interesting, not to spend too much time on this, what is interesting is that we got all the way up to close to 38 million transactions per second, okay, for TPCC, right? And the system is capable of dealing with about 1.6 billion log requests per second, okay, depending on what type of concurrency control you want to do. And again, there is no fancy hardware in here. The only thing that we are doing is using RDMA, which is something that is starting to be using in a clever way to actually minimize the overhead of communicating between machines, which is the problem of distributed locking. So one idea that we want to actually do is we want to do exactly this, but put the log table on the FPGA. And then the reason why we're interested in doing this is that we have developed our own RDMA network stack. So we actually can RDMA directly to the memory of the FPGA, in and out, to either the memory of other machines or to the memory of other FPGAs. And we think we can actually do what we did on the supercomputer. We can do it on a cluster of FPGAs, but we can actually do it even faster than RDMA, where typically we have a latency of about a few microseconds. Here, probably we can do it even faster. And then the only thing that we have to do is actually move the transaction manager, log manager, and so forth, right? I mean, move it to the FPGA, and then actually enable throughput that is very unlikely to be able to reach if you actually trying to do this from the CPU. Okay. So this is an interesting outlook. We are in very interesting times. As the cloud becomes the dominant computing platform, I'm convinced that databases will abandon the conventional architectures, the one that we have had and we have worked for many years to actually build. The architectures in the future will be very, very different. And they will become a far more dynamic data processing platform, highly distributed, with acceleration in all aspects of the system. A lot of components of the system are going to be active in the sense that they can actually process data as well, and so forth, right? And we are back to the design board with most assumptions about how databases should work, about what data processing implies, and so forth, no longer being valid because the platform underneath has changed so much, right? So we are almost at a blank slate, not quite, but we're almost at a blank slate, right, to develop new things. And thanks, Martin, for being such an inspiration all these years. And I hope that there will be not only you contributing, but more people will take inspiration from the work that you have done and your crazy ideas, because I think they are now more needed than ever. Okay, so thank you very much. And if anybody has questions or comments or discussions, I'm happy to answer. Thank you.
Thanks, Gustavo. Thanks for the nice talk. Let me check the gallery to see if there might be raised hands with a question. Oh, no one is raising his hand, so I'm not sure if he has a question.
Okay. So here in the chat there are a few questions. Okay. So Mohan says, in some way, this is like going back to the days of database machines of decades ago. Yes, I mean, in fact, let me just give you an example. Amazon Aurora. right? I mean, so in the cloud. So they have a great system. It works great. However, it is a hack, right? I mean, they took Postgres, they hammered enough so that they could run on the cloud and things like this. You don't need to be a genius to realize that this is not how the system will look 5 years, 10 years from now. Eventually, they will actually go and continue evolving this until the structure of the database will be much more tailored to the cloud. And then this will not look like Postgres at all, right? I mean, these many database companies have done this over the years, right? I mean, so they took an initial database design and then kept evolving, and then until at the end, what they have has nothing to do with where they started. So I think this is what is going to happen, right? And this is just one example, right? Okay. Okay. Sorry?
Holger asked this question: should we be thinking about custom hardware that better supports this aggregation?
So I was looking at another question from Holger that it was about, but I can talk about disaggregation. Yes, disaggregation is something that I also think that is coming. I mean, we have non-volatile memory. Very soon we're going to have non-volatile memory that is attached to the network. At which point the question is, can you actually just work with that memory on the network without having a CPU attached to it? I mean, having what the architects call disaggregated memory. I think that will be very interesting. We are already working on that. We're actually trying to build a disaggregated memory where you can actually do database processing, right, on the disaggregated memory, only to a certain extent, because you do have some limitations. But I think it's a very, very interesting space to actually definitely look at, right? So there is a question from Tamer. Why is there no GPU in your new architecture? Aren't they useful if you want to run IO workloads? Yes, that's fine. The reason why I'm not talking about GPUs, although we are working with GPUs, is because at a certain point you need to focus on something. GPUs actually are very well integrated by now. Let's see. Now the market is also changing, right? I mean, now that NVIDIA has been bought, right? I mean, by a company that actually does a lot of networking. Let's see how actually happens, right? But as I said, there are GPUs, there are TPUs, there are FPGAs, and soon we're going to see even more systems out there, right? I mean,
yes, very interesting. So Gustavo, with that, I think I would like to really thank you once again for joining the CWI lectures and giving this very interesting talk. But
thank you.